Well, so here we are back in the classroom, an actual, honest-to-God classroom. So what we're going to do at this point is we're going to start putting together everything that we've done up to this point. We're going to talk about terminology, we're going to use some math, we're going to talk about the scientific method. We're just about ready to do what would, in normal circumstances, be an honest-to-God, hands-on lab in the classroom. Well, we can't do that, but I can do some demonstrations here. So let's turn to page 45 in the book. We're going to talk about mass a little bit more. There it is, the second most famous equation in the world. So we're going to spend a little more time on mass. Now, one of the ways that we can evaluate mass is to evaluate something that we call mass density. Mass density is an evaluation of how much mass in a given volume you may have. So first, let's do a little review of volume, just in case you're a little bit rusty on volume. We're going to stay metric because, quite frankly, boys and girls, to get into US standard or British, to get into cubic feet and cubic inches and all that stuff, it would be a nightmare. Trust me on this one. So we're going to stay metric. So here we have the representation of a cube that you've seen any number of times in any given math book. So let's say that we have a cube that is 1 meter by 1 meter by 1 meter. All right, and so that would be 1 meter times 1 meter times 1 meter, fill in the blanks in the book, and that would equal 1 meter cubed, 1 cubic meter. Also, let's remember that in 1 meter there are 100 centimeters, so that would be 100 centimeters by 100 centimeters by 100 centimeters, and so that would be 100 times 100 times 100. All right, that would be 10 to the 6 cubic centimeters, or centimeters cubed. Therefore, 1 cubic meter is equivalent to 1 million, or 10 to the 6 cubic centimeters. Additionally, some other stuff here that you'll need to know is 1 meter cubed equals 10 to the third liters, 1,000 liters. You should know that. And 1 liter equals 10 to the third, or 1,000 milliliters. These are going to be important down the road here. All right, so the last bit at the bottom of the page, I put in primarily for first responders and medical types, because this one goes to a trick question that oftentimes shows up on your professional examinations. So I've set up a factor labeling conversion problem to determine how many milliliters there are in 1 cubic meter, and it's already set up, so all you have to do is just do the cross canceling, and we'll see that ultimately 1 cubic meter equals 10 to the 6 milliliters. So since 1 cubic meter equals, right at the last 2 lines on the page, since 1 cubic meter equals 10 to the 6 cubic centimeters and also 10 to the 6 milliliters, now we can say that 1 cubic centimeter equals 1 milliliter, which is also commonly referred to as 1 cc. And the reason, and again, back to the reason why I put that in there, that shows up as a trick question in a lot of the exams. And I've seen this on a number of occasions where an exam question would be, to convert 35 cc's into milliliters. And the examinee will sit there and panic and, oh my God, I forgot the conversion. Well, that's why it's a trick question. There is no conversion. Just remember this, guys. A cc is the same as a cubic centimeter, is the same as a milliliter. They're all the same. Don't forget that one. All right. Mass density calculations. That puts us on page 46. All right. Mass density calculations, also referred to simply as density, is measured in, this is the metric world, is measured in kilograms per cubic meter, or abbreviated like so. Now, I'm well aware that chemistry types and biology types frequently go to density in terms of grams per cubic centimeter. I'm aware of that. But here in physics land, we're going to use the standard units, and so the standard units will be kilograms per cubic meter. Now we need to be able to do conversions between grams per cubic meter to kilograms per cubic, grams per cubic centimeter to kilograms per cubic meter, and back and forth. And there's also a way that we're going to be able to evaluate the mass densities of different materials. So here on page 46 we have an example. Let's say that we have a sample of material that is 67.5 grams, that's the mass, and we determine its volume to be 30 cubic centimeters. What would be the mass density of that material? So we're going to use factor labeling to convert grams per cubic centimeters into kilograms per cubic meter. So we'll start with 67.5 grams per 30 cubic centimeters. All right, that's what we start with. Now we're going to set up conversions. I'm going to change two factors here. I need two factors here, so I'm going to put grams here, cubic centimeters here. I'm going to put kilograms here, cubic meters here. Now the conversions. There are 10 to the third grams in 1 kilogram. Now remember, we just did this, 10 to the 6th cubic centimeters in 1 cubic meter. Now we cross cancel. And we have 10 to the third here, 10 to the 6th here. That reduces to 10 to the third. And now we wind up with 67.5 times 10 to the third kilograms per 30 meters cubed. So 67.5 divided by 30, I get 2.25. 2.25 times 10 to the third kilograms per meter cubed. And that would be the mass density of that material, whatever it may be. Another thing that we can do, turning to page 47, is we can use some of this methodology to predict the mass of a given sample of material. So let's say, here we are on page 47, let's say that we have a 50 cubic centimeter sample of lead. We know that it's lead. We want to predict what its mass will be. So we'll set up a proportionality equation. The first thing we'll do is we will state the known mass density of lead, which happens to be 11.3 times 10 to the third kilograms per cubic meter. we'll set it up as equivalent to the given sample. Our sample is X number of grams per 50 cubic centimeters. Now, we created a problem for ourselves because now we're mixing and matching our units here. I have grams here, kilograms here, cubic meters here, cubic centimeters here. Since I'm dealing with a small sample, the smart money would be to go to small units. So I'm going to convert kilograms to grams, and I'm going to convert cubic meters to cubic centimeters. So kilo, that's 10 to the third. 10 to the third times 10 to the third is 10 to the sixth, so that would make it 11.3 times 10 to the sixth grams over 10 to the sixth cubic centimeters equals X number of grams per 50 cubic centimeters. Now everything matches. What we're going to do now that everything is matched, now we're going to do a little bit of an algebraic razzle-dazzle. We're going to do what's called cross-multiplying. Don't confuse it with cross-canceling. Cross-multiplying. You get to do this when you've got fraction-looking things on either side of an equation. So I'm going to multiply this by this, and this by this, and now I get 11.3 times 10 to the sixth grams times 50 cubic centimeters equals 10 to the sixth cubic centimeters times X grams. Let me just double check to make sure I haven't left anything out. I think I got everything there. Yep, I did. Now, remember this from your high school days with Mrs. Gilhooly's algebra class. What can you do with like terms on both sides of an equation? You can just get rid of them. So, what can I get rid of? Well, I can get rid of grams. I can get rid of cubic centimeters. Oh, I got 10 to the 6 here, 10 to the 6 here. That goes away. Look at that. This is what I mean when I say the way to survive physics problems is to front load your problems with as much no-brainer stuff as you can before you actually start crunching numbers. And we haven't crunched any numbers yet. All we've done is taken out the trash. So now, look what we got left. 11.3 times 50 equals X, which equals 565. In other words, that 50 cubic centimeter sample of lead should have a mass of 565 grams. That's the basic idea. So we'll go through a couple of other ideas here before we actually get into doing a demonstration. Page 48, mass density. Neutron stars are the ultimate in mass density. Let's see, oh yeah. Neutron stars, they're pretty weird critters. They're the leftovers from a supernova. I found this in Goodwill somewhere. I don't even know exactly what it is. Someone told me it was some kind of a trick ball, but it just reminded me of what a neutron star would look like. And yeah, they do look kind of like that. This neutron star is the most perfectly reflective surface in the universe. Anyway, if a star, on page 48, if a star has sufficient mass, that is to say, 8 to 20 times more than our own sun, when it goes nova, the atoms of the remaining material in the core are ripped apart by the extreme gravity and extreme pressure. And during this process, electrons combine with protons to form neutrons. Now, since the volume of a normal atom is over 99% empty space, we've talked about this, is over 99% empty space, this once empty volume is now filled with neutrons. The result is a material so dense that a teaspoon of this substance can weigh 10 million tons, or the same as 100 aircraft carriers. And there you see on the page the illustration of 100 aircraft carriers. Now, for those of you who do venture down here to South Portland, you see these cruise ships going by. They're about half the size of an aircraft carrier. What we're saying is that my little Zippo lighter here, if it was made of pure neutrons, would have the mass of over 100 aircraft carriers. So that's a little bit of trivia for you. Page 49, we'll do a couple of exercises here. Okay, this is where we do a self-check, page 49. We're going to determine the mass, or the mass density rather. We're going to determine the mass density of a 273 gram sample of material with a volume of 35 milliliters. So, how do we do that? First we state what we got. This is what you do in science. You record what you got. Put it on paper. If it ain't on paper, it didn't happen. So we got 273 grams with a volume of 35 milliliters. All right, now we want to get the mass density. That means we want to convert this into kilograms per cubic meter. So we have two sets of units that we want to convert, two conversion factors therefore. All right, I'll put grams down here. I'll put milliliters up here. I don't want grams, I want kilograms. I don't want milliliters, I want cubic meters. There are 10 to the third grams in 1 kilogram. Remember, a milliliter is the same as a cubic centimeter, is the same as a cc. That means that there are 10 to the 6 milliliters per 1 cubic meter. Cross cancel. See what we got. We got 273 times 10 to the third kilograms per 35 meters cubed. $273 divided by 35, 7.8. Now, that is the mass density of this material. It also happens to be the mass density of iron. So the next example, determine the mass of a 95 cubic centimeter sample of iron. So we know that iron has a mass density of 7.8 times 10 to the third kilograms per 1 meter cubed. And our sample is X number of grams per 95 cubic centimeters. So we'll convert kilograms to grams. So kilo is 10 to the third times 10 to the third, that's 10 to the 6th. So that makes it 7.8 times 10 to the 6th grams. While 1 meter cubed is the same as 10 to the 6 centimeters cubed. Now we're set up properly. We have matching terms on both sides. cross multiply. 7.8 times 10 to the 6 grams times 95 cubic centimeters equals 10 to the 6 cubic centimeters times X grams. Double check, make sure I didn't miss anything. I think I've got them all. Yeah, looks like it. Okay, so now let's do some canceling. Grams, cubic centimeters, 10 to the 6. Okay, taking the trash out. Look what we got left. 7.8 times 95 equals X. So, 95 cubic centimeters of iron should have a mass of 741 grams. This is one of the ways that we can identify certain materials. I'll tell you a little sea story here. Some years ago, when I was teaching a summer course, I was in between classes, and we had a lot of contractors working on the campus doing some reconstruction after some storm damage. And this guy showed up at the door and he said, are you a chemistry guy? I said, no. I said, what do you need? He said, well, we were digging around Preble Hall and we found this strange metal. We don't know what it is. We were wondering if you could help us identify what the metal is. So I said, well, let's see what we can do. And I said, let's do mass density on this metal. Maybe that will point us in the right direction. He said, sure. So we really took our time with this one and got it right down to a gnat's ass, and determined what the mass density of this metal was. Now, it was silvery, but it wasn't tarnished. It was kind of heavy. So that ruled out aluminum. It certainly wasn't aluminum. It wasn't rusty, so it wasn't iron. It wasn't tarnished, so it wasn't silver or pewter. So what the hell was it? Well, we figured out what the mass density was, and I looked up in a few textbooks to see if anything matched, and I couldn't. So then I had to go online and come up with a complete list of the mass densities of all different types of materials. And it turns out that this material that they dug up, it had obviously been melted and then solidified. This material was actinium. Now, what was the significance of that? Well, it turns out, now I don't know the full story on this, I don't pretend to, but I have read that actinium, for whatever reason, was a metal that was used in military army hospitals 100 years ago or so. For what reason, I don't know. But it kind of fit, because Preble, what was that? That was an army hospital. This campus was an army base. So yeah, so that's kind of a mystery solved. Jewelers do the same thing when they're trying to evaluate whether it's 12 karat gold or 24 karat gold. It goes to the mass density of what gold is. All right, so this is one of the applications of how mass density works. All right, so we'll stop here, and the next video I'm going to demonstrate how to do mass density. But before we do that, I'm going to do one more thing here, and I want you to take this down. Because we'll be using it in some problems down the road here. I want you to know the mass densities of some different materials. So, aluminum is 2.7 times 10 to the third kilograms per meter cubed. Iron is 7.8 times 10 to the third kilograms per meter cubed. trying to do it in sequence here. Then would come copper is 8.89 times 10 to the third kilograms per meter cubed. Lead, 11.3 times 10 to the third kilograms per meter cubed. And one more, here's an alloy, brass. And there are different grades of brass, but on average it's roughly 8.4 times 10 to the third kilograms per meter cubed. All right, so take a minute and jot these down so that you will have them. And these we'll be using when I demonstrate how to determine mass density in a lab environment. So we'll stop here.